Welcome to Maths with EJD. We are still talking about nonlinear programming, and the focus has been on, we've seen different methods for solving nonlinear programs, right? Um, Nonlinear programming. We've seen a penalty method, barrier method. We've also seen the Contocca conditions. Now we're talking about the evolutionary algorithms. Okay, so we've seen penalty method penalty method. We've seen the barrier method, barrier method for solving nonlinear programs, barrier method. We've also seen the con Karush-Kontokka conditions, which is the generalization of the Lagrangian multiplier. So here we're looking at the evolutionary algorithms, evolutionary algorithms. And under the evolutionary algorithms, we've seen different things. First of all, we've seen the simulated annealing, which is a mimicry, simulated annealing, which mimics cooling in metallurgy. We've actually seen um, taboo search, which uses memory to be sure that we do not visit um, a solution that a possible solution that was visited in the past. Then in the last video, we saw algorithms, genetic algorithm, which takes idea from selection, mutation, crossover, and all that. Now we're looking at swarm, particle swarm optimization. So lastly, we'll be looking at, after that, we'll be looking at differential evolution. So those are all evolutionary algorithms, differential evolution. Okay. And just like I said, right? Um, so we've been looking at all this. We've taken care of simulated annealing, taboo search, genetic algorithm is done. Now we move on to particle swarm optimization. Particle swarm optimization, or PSO. Okay. So what is exactly PSO? What is it? What exactly does it tell us? And how do we use it for solving nonlinear programs? So particle swarm optimization, PSO for short, is an evolutionary algorithm, just like I said now, an computational technique, evolutionary computational technique inspired by social behavior, the social behavior of birds flocking. You have birds flocking or fish schooling. That is fish moving together, basically. And birds flocking, birds moving together too. So birds flocking or fish schooling. So we have a lot of lessons to learn from biology, right? Even for algorithm formation. So, and what this does is that it is particularly effective for optimization problems, for optimization problems, including including nonlinear programming, nonlinear programming problems, right? Nonlinear programming, where the objective function, where the objective function is not necessarily linear. So if everything is linear, we can always do linear programming, which I've done. I have 55 videos on that. You can check the playlist. So it's not necessarily linear and might contain multiple local minima. So making it non-convex in nature, right? Now, in particle swarm optimization, a population of particles, a population of particles. So those particles in this case are like our candidate solutions. Candidate solutions. So in a PSO, a population of particles explores the solution space. So it's like you have all the bed of fish running around. Okay, they explore the solution space by adjusting adjusting their personal positions, by adjusting their positions based on personal experiences. So it's more like a bird is flying and then it's discovered that in a particular location it flaps its wings against another bird, so it doesn't want to go to that place again. So it's making taking position based on experience. So adjusting their positions based on personal experiences and the experiences and the experiences of their neighbors. Okay. All right. So each particle, each particle represents a point, a point in the search space. So each fish represents a point in the search space and moves through moves through it in search of an optimal solution. Okay. So from here, let's look at some key concepts. So key concepts in particle swarm optimization. Okay. Um, First of all, we have particle representation. Particle representation. So here, each particle has a position xi and velocity vi. So the position of the particle is represented as xi, and the velocity of the particle is represented as vi. Okay. So each particle has a position xi and a velocity vi. The position corresponds to a potential solution, while the velocity determines how the position will change during the next iteration. So this corresponds with potential solution, potential solution, that's the position, while the velocity corresponds. So velocity, this determines how the position changes during the next iteration. So that's how we represent particles here. So number two, another key concept is global and personal bests. Global and personal bests. Okay. So for global and personal best, each particle has a personal best. So each particle has a personal best position. Okay. So each bed has a personal best position, PI. Okay. Where it has found the best solution so far. Apart from that, right, for the whole swarm, so the swarm has a global best position G, a global best position G. That is the best solution among all particles. So personal best solution position for each particle, and then we have a global best position for each uh for the whole swarm, right? So it's more like in a country, there are many rich, maybe we have cities, right? In each city, there's the richest man, and they are comfortable in their own skin. Probably they don't even aspire to be the richest in the whole country, maybe. But then, whatever it is, among all of them, there's still one person who is the country's richest man. That's the kind of idea here. So you have global and personal bests. So apart from that, we have the next concept here, which is velocity update. Most of numerical stuff we have to update the concepts, right? We have to update what we are dealing with until in each step of the iteration. So we have velocity update in the case of particle swarm optimization. And the velocity of each particle is updated using the following equation. So we have VI at t plus 1 is equal to W VI at t, okay? WVI at t plus C1 R1 into PI minus XI, plus C2 R2 into G minus XI. So I can see, so this place talks about the personal best position, and this place has something to do with general best position, while this place has something to do with the personal, I mean, the velocity, at the initial time, so to speak. So, so this is really important. This is the equation with which we update the velocity of each particle, so of each one. So again, we need to talk about the conditions. So, or say where W is the inertia weight, the inertia weight that controls how much of the previous velocity, how much of the previous velocity is retained. So if omega is 0.5, so it means that half of the previous velocity will be retained in the next iteration. Okay. Then we also have C1 and C2. Now, if you look at where C1 and C2 are, so these they are like some constant attached there. So C1 and C2 are the cognitive, this is evolutionary algorithm, right? So the bird and fish, they have memory of where they've been and how they are relative to other bird and fish, right? So C1 and C2 are they are the cognitive they are the cognitive and social scaling factors. Cognitive and social scaling factors. So that takes care of the memory of each particle, each bird, each fish, and how they have interacted with others. So C1 and C2 are the cognitive and social scaling factors. Then we also have R1 and R2. R1 and R2 are they are random numbers in the range, in the range of the closed interval 0 to 1. Okay. So that's what R and R2 are. Of course, we already know that the PI are the personal best positions, while the Gs are the global best positions. If I may do that, so that it is personal best position. That's the PIs. And then we have the G, which is just one, right? Which would be the global best position. Personal best positions. Then this is global best position. That's the best position in the whole swarm. Okay. Of course, we have every other thing explained down there. Now, this is really interesting, if I may say so. So, so that is velocity update, right? We also have position update. So we update the velocity and we also update the position. So position update. So for the position of each particle is updated using xi at t plus 1. That's the next iteration is equal to xi at t plus vi at t plus 1. So the velocity at t plus 1 together with the position at t is what gives the position update for each particle. So that's the position update. And then of course we have step 5, we have the stopping criteria. Stopping criteria, which we always would have for numerical situations like this. Okay. Since we are iteratively looking for solutions within we need stopping criteria. So PSO typically stops. PSO typically stops when the when the maximum number of iterations is reached. Okay. Because we can keep going. The space is boundless, so to speak, because everything keeps changing. PSO typically stops when the maximum number of iterations is reached. So if you say we are doing 1,000 iterations, after 1,000 iterations, that stops. Whether it has converged or not, we don't care. So when it is reached, or another thing, or improvement, if the improvement in the objective function, is below a certain threshold, is below a certain threshold. So of course, these are standard stuff. For instance, if the the difference between the value we got previously and now is very tiny and less than the particular value, then we can take it as our stopping criteria. Okay, so let's talk about let's move a bit and talk about PSO for nonlinear programming. Okay, PSO, particle sum optimization for nonlinear programming. So in nonlinear programming, the objective function f of x is nonlinear. I mean, that's to be taken for granted. It is nonlinear, and there might be multiple multiple constraints like gj of x less than or equal to 0 inequality with j equals 1 to all the way to m. Okay. Then the goal is to minimize. The goal is to minimize or maximize f of x subject to these constraints. Subject to these constraints. So PSO can be adapted. PSO can be PSO can be adapted to solve such problems by, first of all, encoding the constraints, into fitness function, encoding the constraint to fitness function. Then, of course, using penalty methods, to discourage particles from moving, into infeasible regions. Okay, we've seen penalty method previously. All right, so with all this said, can we look into some examples? So we're taking two examples here. So we have example 1, which will be solving a nonlinear function, Okay, so consider a simple nonlinear objective function that is f of x equals x1 squared plus x2 squared minus 10x1 minus 10x2 plus 25. That is the function just like that. And then we go step by step. For step 1, we initialize the particles, Okay, so we say let the swarm size, be 10 particles, say 10 possible solutions. That's what we are saying in short. Now we randomly initialize the position and velocity of the particles within a defined search space. Okay, so randomly initialize the positions and velocities of the particles within a defined search space. Okay, then we have step 2. So for step 2, we evaluate the fitness. So the procedures are like the same for most of these algorithms. So evaluate the fitness. So for each particle, evaluate the objective function, f of x at the current position, xi. Okay. And we go for step 3. So step 3. So we're going to do this mainly using Python. So I'm not going to do so much of solving here. So step 3, update. So we have to update the personal and global bests. So that's the best position for each particle and the best position overall. Okay. So if the fitness of a particle at its current position is better than its personal best, update the personal best, right? So if the fitness, what we give you the fitness is if you're maximizing, so after evaluating the 10 possible solutions, so it's more like what we did before. We chose x1, x2, just choose them randomly, x1 and x2, 3, 4, 7, 3, 4, 2, and so on and so forth, and evaluate. So if you're maximizing, you pick the best. If you are minimizing, you pick the highest. Maximizing, if you're minimizing, you pick the lowest. So if the fitness of the particle. So the fitness is basically the value of the objective function you get. So if the fitness of the particle at its current position is better than its personal best, update the personal best. Update the personal best for that particular one. Then next thing is if the fitness of the particle is better, if it's better than the global best and the global best among all particles, update the global best. So it automatically takes the place of the global best. Update the global best. Okay. Then that takes us to step 4. So in step 4, we update the velocity and position. Of course, we need to update the velocity first before we are able to update the position. So first we update the velocity using the velocity update equation like we had before. Velocity update equation. I'll just flash that briefly. So this is the velocity update equation right here. This Okay, this is velocity update equation. Okay, so after that, we also update the so update the position, update the position based on the new velocity. So you know that new velocity is necessary to update the position. So I'll flash that also for a few seconds. So this is the position update equation right there. So you see that at time t plus 1, you need the velocity for t plus 1 and the position for t to update the position, basically. Okay. So with that in place, we go to step 5 where we repeat, like they say, rinse and repeat. So step 5, you repeat until convergence. Repeat until convergence. Convergence. So repeat steps 2 through to 4 until the stopping criterion is met. Okay. So repeat steps 2 through 4, all the steps we've been talking about until the stopping criterion is met. So that's for example 1. So you see, I've not really solved anything because imagine if I'm going to take 10 particles and their positions and how it's changing. That's going to be a lot of work. So, but we're going to use Python to take care of that. So I'll just write the second example and then I'll show you the Python code for everything together. So now I want to go this and say this. Does that work? Yeah, I think it does. But let me go back to this. Yeah. So example 2. So this time around, we are talking about constrained nonlinear programming. Constrained nonlinear programming. Okay. So here now, consider to minimize f of x equals x1 squared plus x2 squared subject to g1 of x equals x1 plus x2 minus 1 less than or equal to 0. And then you have g2 of x equals x1 minus 2 less than or equal to 0. Okay, so we can begin to deal with this step by step. So for step 1 now, so we want to use particle sum optimization for this. So step 1, as usual, is to, first of all, so since we have a constraint problem now, we have to penalize infeasible solutions. Penalize infeasible solutions. So that's more like we are doing penalty method. And the way to do that is to say, so we say a penalty function can be used to incorporate constraints into the fitness function. So that means we have f penalized of x now is equal to the objective function f of x plus the uh the the penalty parameter, right, multiplied by summation from j equals 1 to m, and then of the maximum value of 0 and the constraint gj of x all squared. Okay, all squared. Okay, so that's the idea of penalty. I mean, if you've not seen the penalty method video, please, you can check that for a comprehensive explanation of penalty method. So that's step 1 right there, and we go for step 2. So in step 2, we're applying PSO. Apply PSO. No, the application of PSO has been explained up there, right? So apply the PSO algorithm. So the PSO algorithm, like the 5 steps we did for the first example, that's the same thing. Apply the standard PSO algorithm. Okay. But now evaluate. So you evaluate the penalized fitness function. Penalized fitness function, which is the f penalized of x instead of the original objective function, because here now the constraints are involved. So you use the penalty function to make everything into just one function instead of the original objective function. Okay. So what this does is that it will guide will guide will guide the particles. So the penalization is guiding the particles to explore feasible regions while avoiding infeasible regions, while avoiding infeasible regions. So basically, the idea here is that the penalty parameter is there so if you are going to stray, you are going to pay so much for that. As a result of that, the particles stay within their space. For instance, imagine that you have a fish pond, maybe a very large fish pond. No matter how hard the fish try, they cannot swim beyond the fish pond. So you have put a penalty around them, like, or maybe there's an electric wire or something for birds. Like if they try to go up beyond the particular point, maybe they get a little electric shock that cannot harm them or something like that. So those are some scenarios we can see. So let's go and see the Python code that deals with these two problems. Yeah. So here for the first one, we have the the nonlinear expression like that, with the equation at the very top of that. So x1 squared plus x2 squared minus 10x1 minus 10x2 plus 25. So here we define the expression in line 7, and then the number of particles we say 10, number of iterations we say 100. We can increase that, we can reduce it as we like. Inertial weight, that's 0.5. C1 is cognitive factor, C2 is social factor. We can change these values as you like. And then we have to we initialize the particles. So that's what's happening here, and it's taking some random function. And then PSO algorithm with visualization. So you have so you can study this later, copy it from Facebook and see what exactly is happening there. So we have all the updates for the velocities and particles right here. And then we can run this and see what the result looks like. Okay. Now you can see it really looks like fish or bird flying around and fish swimming around. And at the end of the day, it looks like the best solution for the first problem, for example one, right? For example one, so it looks like x1 is roughly 5.0, x2 is also 5.0, because 4.999 something is 5.0. So that at the end of the day, we have f of the best value of those two, of x1, x2, would now be minus 25. That's for the first problem. And for the second problem, which is a constraint optimization problem, now see, the problem is defined here too, and we also have the constraints, in lines 11 and 14. Then we have the penalty imposed now to make the problem into one. And then we have number of particles, still 10, number of iterations, 10. And we have the inertia with still 0.5, C1, C2, cognitive and social factors, still C1 and C2, 1.5 apiece. And then, we still have the updates for velocities and particles and all of that. So at the end of the day, we just run and get, so you see, this is also, so now we have constraints for this. And then here we have answers that are very close to zero. For example, two, everything looks like 0, 0, 0, because this is the first one is minus 1.355 raised by 10 raised by minus 8. So we can say x1, x2 is like 0, 0, while the best objective function to f of x1, x2 is like 0, because that's 4.45 times 10 raised by minus 7. That's 0. Like 16 zeros before we reach the first significant number. Okay, so that's how that goes for the two problems. So we can go back to what we've been doing and talk about what the Python code has told us about the two examples. So we say for example one, for example 1, we have x1, x2 to be equal to 5.0, 5.0, and the function overall, f of x1, or we can just say f of x if you like, that's simply minus 25.0. Okay, so for example, so that's from the Python code, right? So from the Python code, so for example 2, we have x1, x2 to be equal to 0, 0, and f of x, that's f of x1, x2, is also equal to 0, basically. And what do we learn from this? So we see that particle sum optimization is an effective algorithm for solving nonlinear programming problems, including those with constraints. The flexibility of PSO lies in its ability to handle non-convex objective functions and complex constraint structures. So by updating particle positions based on both individual experiences and the experiences of the swarm, particle sum optimization can converge to an optimal or near optimal solution in challenging optimization landscapes. On that note, we can then talk about one or two practice questions. Let me see the one I would really like. Have quite a number. Okay, still searching. Okay, I guess. Should I do this? Okay. Yeah, I mean, this is a bit challenging. This is multi-objective PSO. So let's see how we can play with this. Multi-objective particle sum optimization. So solve a multi-objective problem where you aim to minimize, conflicting objective functions. Okay. So you have f1 of x to be equal to x1 minus 2 squared plus x2 minus 3 squared. That's the first objective function. And the second objective function, f2 of x, is x1 plus 1 squared plus x2 plus 1 squared also. x1 plus 1 squared plus x2 plus 1 squared. So use a multi-objective version. Is a multi-objective version of PSO to find Pareto optimal. And I didn't talk about this. So if you want to do some research to get this, but I've given the basic idea of this whole thing. So here's the multi-objective version of PSO to find Pareto optimal set of solutions. Okay. So we have for the set parameters, we need parameters, right? For the set parameters, okay. For the set parameters, let's say swarm size. Take swarm size to be 15. Then take maximum generations to be 50. Then so apply the concept of Pareto dominance. So you want to check up what that is about. Pareto dominance to compare the solutions. Okay. Then C, plot the Pareto front, and analyze the trade-off. Analyze the trade-off between the two objectives. So this feels like some kind of project. So you want to try your hands on that. Let's see what you get. Feel free to let me know what your findings are in the comment section, either on Facebook or on YouTube. Of course, you can get the Python code only on Facebook because I'm not able to put it on YouTube. And also let me know if there's a topic you'd like me to teach or a problem you'd like me to solve and how helpful these videos are for you in general. Let me know all of that. And of course, if you have not subscribed, please go ahead and do that. If you have, thanks a lot. And for everyone who has either subscribed and who is just subscribing now, be sure to hit the notification bell so you can always get alerted each time a new video is released. Then don't forget to like and share so that more people can have access to this great content. So like come your way again, keep doing maths right. So in the next video, I'll be talking about the last method I'm going to talk about as far as evolutionary algorithms are concerned, and that is differential evolution. And afterwards, we'll be talking about differential equations. I know a lot of people have been looking forward to me talking about differential equations. So it's about time. We are just one video before we get to differential equation. Interestingly, we are looking at differential equations after differential evolution under evolutionary algorithms for solving nonlinear programming problems. Bye.